What is going on, YouTube? I hope you all had a wonderful Memorial Day weekend. I hope that your current week is going just as splendid, but I figured we'd do a quick little recap to make sure that we are all on the same page. You have not seen the schematic yet, but it should look familiar because we went up to about this point on it. This is an actual schematic of the whole of the amp, obviously a JCM 800. So this should be somewhat familiar to you. Now, if you aren't up to speed with me yet, let's just do a quick little recap. These little ziggy-zaggy lines, those are resistors. That's what they denote. These two little things that look like little bars facing each other, those are capacitors. And then these little triangle things with a little line that they point towards is a diode. All right. Now, on this particular schematic, they're using nanofarads to denote all of their capacitors. So there are converters online if you're not familiar, but it takes some time to learn this. Picofarads are almost always going to be in picofarads. So 470p is always going to be 470 picofarads. But 22N or 22 nanofarads is the same as 0.022 UF, okay? So UF and MF are the same, but 0.022, the 680N, 680 nanofarads, is the same as 0.68 UF, okay? So just to kind of clarify that, spend some time to learn those because it can... Nanofarads isn't as popular when you go on to like these different places. Like if you go to Antique Electronic Supply, it's not going to say 22N, it's going to say 0.022 UF. So you're going to need to convert some of these things around a little bit in order to make it easier to find some of them. Okay, that's why I'm just kind of going over that. So let's follow along real quick through this schematic here, and we'll talk about a couple things. So we go in through the high input. You'll see it goes through this grid leak here, the 1 meg grid leak, then through a 68K grid stopper. That goes into the grid of this tube, and it goes up out of the plate. And then it goes through a coupling capacitor, 0.022 UF, which then goes through the low input jack. Okay, so when there's nothing plugged into this jack, it will go through the tip portion of that jack and on to the next preamp stage. Conversely, if you plug into the low input jack, it will raise this connection up and away from this portion of the circuit, taking this out of circuit. Okay? So that goes through this little network here, into the volume, of course, and into the cold clipper stage. The cold clipper stage is cold clipper because it has a very, very high relative cathode resistor. What this does is it offsets the bias of this tube, and when the signal comes in, the lower half of the signal, the downward swinging side of the signal, will distort or clip before the top half does. This creates a nice, soft, asymmetric type of distortion that is just kind of mellow, smooth, and it's pleasing to the ear, and it's a big part of what makes this amp tick the way that it does. It gives it kind of that characteristic sound that this amp is known for. So it comes up out of this plate into another 0.022 UF coupling capacitor and into another voltage divider network. This network right here is dumping half of the volume that is produced by this tube away before it gets to this stage. They're using a treble peaking network here, or a treble peaking cap, if you will. It's a 470 picofarad, and that's letting quite a bit of the mids and highs go over the top of this resistor. That is going to make this amp a little bit brighter, a little bit brasher, and give it some more of that grit. You can remove this if you want. A lot of people do. Some people will even remove this one. That'll mellow it out a little bit, make it a little less bright, a little less brittle. But that is up to you if you want to do that or not. I say build it like this first and then see where you sit with it. It's going into a pretty hotly biased, the next stage is pretty hotly biased. 820 ohms, this stage is pretty warm, or warmed biased, if you will. And then it goes into a cathode follower. We talked briefly about what a cathode follower is for. We mentioned that you can go off the plate of a tube or you can go off the cathode of the tube. The cathode of the tube, if you go from there, will have a little more drive, a little more push to get through lossy tone stacks and stuff like that. So this particular tone stack has a pretty large amount of insertion loss. Insertion loss just means that it's going to load down the preceding stage, and what comes out the other end just might not be, it just won't have the snot, let's just say, that it came into this side of the network. So with the cathode follower, it has a little more snot to get through to the other side and drive the next stage after that. Whereas coming off the plate, this would change how this network works. So it would change how this all interacts, and it would obviously suck a lot of drive away to get into the phase inverter in this instance. So here we go into the phase inverter. We got another 0.022 coupling capacitor here. Goes into the phase inverter. Up in here, you'll notice that it's got a snubber, is what they call it. It's a 47 picofarad ceramic disc cap. What that is there for is to control or eliminate the highest of the highs. Common mode rejection, we talk about that. These are out anti-phase here, so they're out of phase from each other. So when you try to connect them together, they will cancel each other out. This creates a shelving filter, and this knee that is created by this and the other parts of the circuit there will shunt or cancel out frequencies above a certain point. So this is getting rid of just the air of, you know, the highest of the high fizzies and stuff like that. You can play with that value quite a bit. A little goes a long way here, but you can play with that value to kind of dial in or out how much fizz is getting into this circuit. So then it goes into the coupling capacitors for the output section, 0.022. Once again, there's a lot of them in this amp. And then it goes into the 5.6K grid stops, which is also 5K6. We talked about that. If you see a 5K6 or a 1K2 or 2K7, it simply means 5.6K, 2.7K, or 1.5K, or something like that. Okay? From here, it's going obviously into the output transformer. And then from the output transformer, you notice we got something going on over here. This is the feedback loop. It's part of the present circuit. This one, they're feeding it off of the 4 ohm tap, it looks like. That looks to be correct. So the 4 ohm tap is driving the second input of the phase inverter. So a long tail pair phase inverter like this one here has two inputs. We got the one here that the main signal is coming into, and then we got the other input which is being fed the presence or the feedback loop. This signal here is out of phase with this input here. So it will try to cancel out the frequencies that exist that you send into there, right? So that's what this is doing, is it's creating a voltage divider network, and it works in the opposite way that you think. So as you dial the presence up, it's actually shunting more signal away to ground, making it not go into the phase inverter. So it's pulling signal away from the phase inverter, and that's what makes it brighter. Okay? So it's allowing less frequencies to go into the phase inverter. If you were to remove the feedback circuit of this amp altogether, it would be very, very bright, very, very brash. You might not even like it at all. The feedback loop in this amp is a big part of what makes it work the way that it works. Now, conversely, if you dial the presence out, you turn the presence down, what it's actually doing is holding this signal up away from ground more, driving more of that signal into the other side of the phase inverter. Obviously, more signal in means more cancellation. More cancellation means darker sound. So that's how the presence works. So when you're turning the presence up, it's not actually turning it up. It's actually shunting more of that signal away from the phase inverter to do less work. And as you dial the presence down or turn the presence down, it's actually sending more signal into the phase inverter, causing it to cancel more. All right, so now that we got that, here's the bias circuit. We kind of briefly touched on that. This is a pretty important portion of the amp. This is a fixed bias amplifier. It is not cathode bias. So you do have to make sure that this circuit is done correctly. This value right here will kind of change the range that it'll work within. So if you need to change the voltage, you know, where the voltage is setting at for the negative voltage supply, it says here that it needs to be minus 57 volts. Let's say you're at minus, you can't get up to minus 57. Let's say you need to change this value here in order to adjust that to get into that point. So enough of that. But this creates a negative bias voltage right here. Power section, they're using a double pole single throw switch, so they're cutting both the line and the neutral. I like that. That is a classic Marshall thing to do. It goes through the fuse into a voltage selector, which allows you to get the right primary voltage for the country that you are in. On the secondary side, they're breaking the standby on, they're using another double pole single throw switch because they're breaking both of the things, not just the one side, which is, they kind of have to in this instance. But in either case, it goes through the diodes. This is the bridge rectifier here, into the reservoir cap, through another fuse, the HT fuse in this case, to the B+, which feeds the B+ rail. And I mentioned we were going to talk about this a little bit more in the first video. Here you'll notice something we haven't seen yet. This is a choke. You can also use a resistor here. A lot of people do, but there's a difference between the way a choke works and a resistor works. A resistor has a higher DC resistance, and it will cause more sag, so it resists the inrush current that is needed to power this section. So when you have this all cranked up and you hit that big power cord, it'll draw down a lot of energy, and it'll cause an inrush of current to need to come into this section to resupply it. Well, that resistor here will resist that inrush of current and will give you that characteristic sag, or kind of swell of volume, if you will. A choke is less prone to that. A choke does really good at getting rid of noise, though. It gets rid of ripple off the power supply better than a resistor will. But it doesn't, it handles the inrush of current better. And that will make the amp sound stiffer, more immediate, more just abrupt, if you will. So you can play with that. You can actually use a resistor in parallel in order to kind of get the best of both worlds. So that is a topic for another discussion, but you can either use a choke here of varying values. You can use a 5 Henry or 10 Henry or 20 Henry or something. That value will change how this choke works with the amplifier. And then of course you can use a dropping resistor, which is like these guys here, these 10K 2 watts. You can use a dropping resistor to introduce sag if you'd like. So over here, because a choke has a very low DC resistance, you'll notice that the voltage drop on either side of it is very low, a volt in this instance. With a resistor in this position, this voltage here would be a lot lower, and you can tell that it would be because by the time you start here, go through this dropping resistor and decoupling capacitor node, it drops a fair amount of voltage, about 50 volts. And then as the current demand becomes less and less, because as you go further in the amp, there's less and less tubes that need to be supplied by the different sections, the voltage drop will reduce because there's less current to cause the voltage drop. So they're using 10K 2 watts all the way across, and then they have these different decoupling capacitors, and each one works for each half of the thing. Okay, so this decoupling capacitor is for this half, this one is for this side. You got this one here, which is controlling this side of it here, and then of course this one for this half over here. So the decoupling capacitors smooth out ripple, and you'll notice that over here on the very ass end, driving the preamp stage, that they're using a higher value, a 60 UF. That's pretty high. 60 UF is definitely trying to smooth out a lot of ripple, and it's also going to make this section be a lot firmer. Usually people will say more bass, firmer bass, solid bass, whatever the heck you want to call it. This amp is pretty solid anyway. 50 UF on this end here this amp is no slouch by any means. So the way that they're doing this, like this one here, they've got 100 UF versus of reservoir cap because they're taking 250 US in parallel. So it's 100 UF worth of capacitance there. And then here, kind of the same deal. It's 50-50, but still 50 UF on either side of this thing. That is a pretty firm power supply that they're trying to create here with very, very little ripple. They're trying to get as much noise as they can out of the power supply, which is a good thing because this is a high gain amp. This tube right here, these two tubes right here are doing a lot of work to try to amplify signal because it's only got to go through one more stage. This is a unity gain stage right here. This one's not really distorting like you would think it would. This one is doing all the distortion. This one is unity gain. So whatever this one's producing, it's the same coming out of this guy. So there's really not much distortion here. It does create a sound. Cathode followers do have a sound. Some people like them. I do not. I'm not a fan of cathode followers. Just saying. But so that's kind of how the power supply works. So these decoupling capacitors make it so that this section right here is separated from this section here, okay? And that makes it so they don't really crosstalk to each other. And then, of course, it also gets rid of the ripple. So it smooths out the power supply, and it does so it cascades, so it gets smoother and smoother and smoother as you get towards the input section of the amplifier, which is the most sensitive and most important portion of the amplifier. Alright, so now that we got that out of the way, if you can understand and read this schematic and how the signal flows and what's kind of doing what and how it works, yada yada yada, then you can do this. All this is for you when you create a layout is a paint by numbers thing for you. It just makes it so you know where to put all your stuff and how to fit it into the amp and make it look like that. So that's it. That software, DIY Layout Creator, is not quite as pretty as this one, I don't think. I think you can probably try and make it this pretty if you wanted, but there's a couple things in this layout I'm not a huge fan of. I don't like kind of stuffing parts together like this, but you know, this will work just fine and dandy. This is a pretty atypical way of doing this, and you can obviously follow this thing through the, you know, you can follow it against this circuit and it makes sense. So this is a very good, clean layout. However, moving forward past this point, you're going to be building your amplifier. For the love of God, do not be this guy and build your amp like this. This guy spent some good money on some parts. It looks like he's got some Sprags in there. Those aren't cheap. He's got some Sozo caps in there. Again, not cheap. We already went over that in the last video where we were looking for parts. This is atrocious. Don't be this guy. Spend some time and try to at least make your lead straight or something. Like put half a minute worth of effort into your build. You want it to look like this. You can see how much cleaner this build is. The only thing it costs you to do this type of a build is time. This was thrown together as fast as you could. I just want to make this work because whatever. I just want to I want a 2204 for, you know. Do not be this guy. Be this guy. On this one here, you can see he changed the layout a little bit. It's not exactly the same. What I do like about his build is that he's actually not using okay, so this guy right here, this 0.68 UF, this guy right here, he's not using a polarized cap. You don't have to use polarized caps in those positions, just FYI. But you'll notice that they get very, very big as you start trying to get into that range. This is 160 volt. That's a little extreme for that position, but this is better than using a polarized cap for that position. So this should sound actually really, really nice. But you can cleanly see what's going on here. You got the 0.022 coupling capacitors, the plate resistors that go for here. You got your 68K coming in. This right here, you can see how they're tied over the top of each other. That's the 500 or 470 picofarad going over the 470K. That's this network right here. Okay. So it's easy to see what's going on. This guy right here is part of the tone stack. Oop, wrong one. That's this guy right here and how it diverges off. So this is going off towards the treble potentiometer here. So these ones here will go off to the treble cap. So the only thing real quick, you'll notice he did not use a bus bar here. So all of his grounds, like this one here, is actually going to a bus bar underneath the turret board here. Love that. Very clean build. The only thing I don't like about this build is how he came off the turrets. I don't really like using super duper long leads like this. That's just a personal preference. Obviously, as you try to suck these things into the next row here, it gets a little bit tighter. So it gets more difficult to do these kind of layouts here. I talked about that in mine where I compromised on doing it the other way so I could go out the other way. And I do that to make the runs a little bit shorter. So this one here, you know, this wire right here has to go all the way up and in and then up through the turret board and then over to this thing. So he's got an extra, what, half inch or more of wire when he could have just gone off the top and then into there. So objectively, you want to try to get these runs as short as practical. It's probably not that big a deal. It probably does not matter that much. Obviously, just trying to go straight over, it can't work. You need to have some sort of space. But this is a very clean look. But doing that is probably the only thing I could knock. But look at how the wires are all nicely, they're like the right length. They're tied together, they're clean. This is how you want to build your amp. He went a little crazy over here. He's got some bias ports here so you can check the bias of the amplifier. You don't have to do that, but this is how you want to build your amps. Don't be this asshole. That is disgusting. Don't do that. Do this. In either case, I hope this helps. Again, just to kind of recap, if you can visualize this and see the signal and understand what's going on, what the parts are, then you can build this. And if you can build this, then you can most certainly build this. Don't fucking do this. All right. Thank you guys so much. Take care. We'll see you on the next one. Bye.